Our next item of discussion is what is called Descartes' rule of signs. Descartes' rule of signs is going to help us when we go to try to factor polynomial functions. Descartes' rule of signs works with polynomial functions with real coefficients, and it tells us that the number of positive real roots is equal to the number of sign changes in f of x or an even whole number less than that. The book says an even integer number less than that, but we're going to find out we don't want to have negative numbers, so I'm going to call it a whole number. And it tells us that the number of negative real roots is equal to the number of sign changes in f of negative x or an even whole number less than that. And my even whole numbers, I mean, I'm going to subtract 2 from whatever number I get here, subtract 4, subtract 6, until I get down to 0. Or if I was going to get a negative number, I'm not even going to include that negative number because I can't have a negative number of real roots. So what I'm going to do is analyze the number of sign changes in f of x, and then I'm going to analyze the number of sign changes of f of negative x. So that will give me my positive real roots. That will give me my negative real roots. And we learned from the factorization theorem that I have the exact number of roots as the degree, and anything that's not a real root will be a complex root, so I'll be able to determine the number of complex roots. We should also remember that complex roots come in conjugate pairs, so there has to be an even number of complex roots. And that's why I'm going to be subtracting even numbers from these to take into account the possibility of complex roots. So I'm going to use Descartes' rule of signs on 3 separate polynomials, and I'll actually make these functions instead of expressions so that you can see examples of how this analysis may help us out when it comes time to finding zeros of polynomial functions. So, the first example says I need to analyze the following function. F of x is x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60. And I want to analyze this for just for f of x. So what I'm going to do is I'm just going to write down the signs. So this will be my positive real roots by analyzing f of x. So I'm just going to write down the signs for each of these terms. I have a positive, a negative, a positive, a positive, and a negative. And now what I'm going to do is count the number of sign changes. Going from positive to negative is 1. Negative to positive makes 2. That stays the same. And then positive to negative makes 3. And then I'm going to subtract even numbers from it. So the first even number is 2, so I'm going to subtract 2 and get 1. If I subtract 2 more, I get negative 1, which doesn't make sense. So I'm either going to have 3 or 1 positive real 0 for this function. To analyze the number of sign changes for the negative function, I need to put a negative x everywhere there's an x. So f of negative x equals negative x to the fourth minus 3 negative x cubed plus 6 negative x squared plus 2 times negative x minus 60. Let's simplify this. A negative number to an even power is a positive number, so this ends up with x to the fourth. A negative number to an odd power is a negative number, and then a negative times a negative is a positive, so that gives me 3x cubed. A negative to an even is a positive. Positive times positive is positive 6x squared. Negative x times 2 is negative 2x minus 60. Notice that when I have an even power, the signs are the same. And when I have an odd power, I change the signs. We're going to use this as a shortcut to do our analysis for negative functions for the next one. So same steps. Write down the sign of the coefficient. Positive, 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 negative, negative. Want to analyze the number of sign changes. So positive stays the same. I changed once, and I stayed the same. So I'm either going to have only 1, because if I subtract 2 from this, I'd get negative 1. And here's where the analysis comes in. I know I am going to have a total of 4 roots. Some of them can be real, and some of them can be complex. So what are my possibilities for, and actually I'll call these imaginary roots instead of complex, because these are all complex again. So let's look at my possible combinations. We saw that we could have either 3 or 1 positive roots, and I could have 1 negative root. Okay? Well, I need my total to equal 4 for all of these. So if I have 3 positive and 1 negative, I am going to have 0 imaginary roots to give me a total of 4. If I have 1 positive and 1 negative, I would have to have the 2 imaginary roots to give me the total of 4. Here's where this is going to help us for factoring polynomial functions. We know we have to have a negative root. The other thing we know is that if we find 2 positive roots, we are guaranteed to find a third positive root. Or if we find 2 positive roots, we know that we're not going to have any imaginary roots. So we can use Descartes' rule of sign to help us use reasoning to find roots of polynomial functions so that we can sketch graphs of those polynomial functions. I'm going to do 2 more examples. My next example is f of x is equal to 3x cubed minus 5x squared plus 6x minus 4. And I'm going to show you how I do the Descartes' rule of signs. What I'm going to do is I am going to make 2 rows. One for positive and one for negative. The first thing I do is I write down the sign of the coefficients as they are written down. Positive, negative, positive, negative. And then for the negative one, I change the sign where x has an odd power. So x is an odd power here, so it changes. An even power stays the same. An odd power changes. An even power stays the same. And now I do my counting. I have 1 sign, 2 sign, 3 sign changes. Subtract even numbers from 3. 3 minus 2 is 1. If I go to subtract again, I'd get a negative number. It doesn't make sense. Here, I have 0 sign changes. What this tells me that I will not get a negative root to this polynomial function. It means I will never have an x-intercept that is a negative number. Then I make a table. positive roots, negative roots, imaginary roots, and my total. My total has to equal 3 because we know the maximum number of roots is the degree of the polynomial. I have either 3 or 1 positive roots. I have 0 negative roots. And 3 plus 0 is 3, so there would be 0 imaginary here. And if I have 1 positive root, I'm going to have 2 imaginary roots to get my total of 3 here. So here's where this is going to help us. It'll help tell us that, hey, we're never going to plug in a negative number in our synthetic division to try to find a factor because we know we will not have any negative roots for that polynomial function. Last example. Says negative f of x is equal to negative 2x cubed plus 5x squared minus x plus 8. Make my 2 rows of signs. I just copy the coefficients for my positive row. Negative, positive, negative, positive. For the negative row, I change the odds. X cubed is odd, so I change it. X squared is even, keep it the same. X is odd, I change it. X to the 0th is even, so I keep it the same. Count my number of sign changes. 1, 2, 3. Subtract 2 from that, I get 1 and 0. And I will have the exact same table that I had in the last problem. For positive roots, I either have 3 or 1. For negative roots, I have 0. Therefore, for imaginary roots to give my total to equal 3, there will be 0 in this case, or there will be 2 in that case.